Okay, so now for the meat to go with the potatoes of the power functions.
Yes, so we need to state the power and constant of variation for the function. We want to graph it and analyze it.
The analyzing is super important for this course in general.
Right, it's something that we do a lot is we analyze functions. Now, in the problems in your book, it specifies that the way we want to analyze it is similar to what is shown in example 2. So if you're like, where are they getting all of this stuff for us to analyze? Look at example 2, and that's where it's at.
And when you're asked to analyze, when you are
asked to analyze,
you will need to include all of these things.
All of these things.
All of them.
There's 9 of them.
That's a lot of things.
Okay.
So here we go.
State the power and constant of variation. So let's rewrite this as something that looks more like a power function. The cubed root of x is the same as x to what power?
The 1/3 power. I know that one.
Right, and the 3 comes from this little number right here. Because we're not squaring x or anything, x is to the first power. That's why there's a 1 on top. So now this looks like a power function. What's in front of x to the 1/3?
I know exactly what's in front.
Yeah?
Yeah, there's only one of them.
So it's 1x to 1/3. Okay, so let's state the power.
Power is 1/3.
Right.
Constant of variation is 1.
Now I'm going to abbreviate the constant of variation as k, because remember we've been talking
that's
about
what we've been using.
That k is typically the constant of variation, and you said it's 1, right?
There's only one.
There's only one.
There's only one.
Now we're gonna graph this. So just throw this into your calculator.
Yep, and take a peek. And hey, it's on the screen.
But yeah, right there. Is it gonna? Right.
Yeah, right.
I mean, yeah,
wow,
it's right
there.
there.
It is. Okay.
Okay, so let's analyze it. And so on example 2, and if we go through, the first thing we need is domain.
So the domain on this guy happens to be all real numbers because there's really nowhere that we can't take a cube root of something.
Right. There's not anything you could plug into x and not get an answer. And if you're looking at the graph, you'll see it continues to go to the left and to the right forever.
And
the
ever.
Whole screen.
It's like it's married forever and ever.
Right. So domain, -infinity to infinity, all real numbers. Then we want to look at the range. So range is our y values. Now, again, you may be a little skeptical of this, but that graph continues going up and to the right and down and to the left forever. No. So it could get to, in theory, -infinity.
It'd take a long time.
Right. But if you kept like scrolling over, you could get bigger and bigger numbers.
You'll never run out of y values.
Right. So our range is all real numbers as well. Now let's think about, how about continuity?
Continuity, great question.
Okay. Is it continuous?
Can you draw this graph from left to right without picking up your pencil?
I can.
I can too.
So it's continuous.
Must be.
Continuous is hard to spell. Because they're like U-O-U. Like,
yeah.
Like, okay.
Yeah.
What's after continuous?
After continuous, let's go with, how about asymptotes?
Okay, so asymptotes, if it's a continuous function, there must not be any asymptotes.
Must not be.
Because we'd have to pick up our pencil for those asymptotes.
You could have a horizontal asymptote.
Oh, right, but there isn't one.
But there isn't one on this guy. Even though you're tempted to say, and look at this graph and go, hey, there's an asymptote when y is 3 or -3. That's not true.
Because we keep going up, we keep going down.
We can find those values that are larger than that. There are no asymptotes.
How about we find Extrema?
How about Extrema? Do we have any peaks or valleys?
Nope.
No none
Extrema.
that I see.
How about increasing, decreasing, or constant?
You know what? I think it's increasing from -infinity to +infinity.
You're absolutely right. It goes up the whole time that we're drawing it. And so we could write this one in 2 ways. You could say increasing from -infinity to +infinity, and that would be a correct way of saying that. Or you could say it's increasing on its domain.
Increasing on its domain.
Because its domain is -infinity to +infinity.
And it's increasing the whole time.
And it's increasing the whole time. So one of those two situations.
That sounds perfect. Okay, we're gonna take it. Oh, sorry about that. Back out of here.
Okay.
So we're increasing on the domain. Are we decreasing anywhere?
No.
No.
If we're increasing everywhere, we can't be decreasing.
We can't be decreasing.
What else do we need? How about
bounded?
Bounded. It's not bounded because we can get all the way up to positive infinity and -infinity. Sorry,
so it's not bounded.
Not bounded.
Another way to think about bounding is to think about, hey, is there a ceiling or floor that kind of is a barrier to our graph that we don't ever go through?
And there's not in this case. It just keeps going up, keeps going down, forever and ever. How about symmetry?
Symmetry, very good question. This guy happens to be symmetry with the origin.
Yes, symmetric about the origin.
Yeah, good guess. I love it when I get those guesses right.
It wasn't because you know what you're talking about?
It was totally because I knew what I was talking about. You know how you can tell if you're symmetric about the origin? I bet you don't know.
Go ahead.
If you like spin the thing around 180 degrees, it'll be the exact same thing.
What's in your first quadrant should be the same if you rotate it around as what's in the third quadrant.
Yes, exactly
And
the same.
if you look at the graph, which you
You
are
should be
right now,
seeing, yeah, it's right there.
right there.
Yeah.
Okay. And then I think we just have in behavior left. Let me count 1, 2, 3, 4, 5, 6, 7, 8. Yep,
9.
just in behavior.
In behavior.
Okay.
What is in behavior?
Well, it means as x is going towards infinity, what's happening, and as x is going towards negative infinity, what is happening. And the way we are going to write in behavior for the rest of our lives from this point on is with limits. So
Limits are super important in calculus, which is why we're going to try and really stress them a lot this year.
right, to get you prepared. The limit as x approaches negative infinity of our function. So I'm just going to write f of x, but you could put
X to the 1/3 or a cube root of x.
You could put your function there. But what we're saying is as we're going towards negative infinity, so as we're going to the left, what values are we approaching on our graph?
Positive infinity?
No, we're going towards
Oh,
negative
dang it.
infinity.
Negative infinity.
Because our
Shoot.
graph is going down and to the left. So
That's what I meant to say.
Yeah, that's what you meant.
Yeah.
Okay, and now we do x as it approaches positive infinity.
Because that's what the graph shows.
Okay, the positive infinity, you're going to the right, and as you do that...
I've got this one.
Yeah.
Positive infinity.
Positive infinity.
Oh, yeah.
Goes up and to the right. That's our first function that we're analyzing. Let's do another one.
Oh, that was so much fun. How could it get any better?
If we do another one.
Let's do it.
Okay. This also needs to change forms by moving the x squared up. We said we changed the sign when we did that. So that's going to be 1x to the negative 2. Go ahead and graph that. And we've got all kinds of stuff here.
So let's just do this real. Back at it again. Sorry about that. So the power. I've got the power.
Okay, then what is it?
Negative 2.
Negative 2. I wonder, am I even still in the webcam shot?
I bet you are.
Okay.
Okay.
K, our constant of variation is?
1, because how many of them x to the negative 2's you got there?
I only have 1.
Yeah, 1 it is.
Yeah, so now we have all these things that we need to do.
All of
the analyzation again. So domain, but this time it's a little more interesting.
Quite a bit more interesting, actually,
Right.
because what one value can you never, ever double stamps have in the denominator?
A 0.
Yeah, because then, life just goes.
You can't divide by 0, and you know why? Because
cats and dogs will start living together. Sheep and lions.
Well, here,
biblical
let's say,
apocalypse.
Let's see. Let's say that we did 5 divided by 0. We're saying take 5 people and put them into 0 groups.
That's easy.
No, you can't do that.
What?
You can't take 5 people and put them in no groups.
So it is it's up like an apocalypse. If we
exactly.
Can do this. Okay,
We're basically causing 5 people to not exist, and that's not okay.
That sounds horrid.
Yeah. So.
All right. So the domain then would go from negative infinity to, but not including 0.
Right, because we're saying we cannot have 0.
And it would go from 0 to infinity because we can't include 0.
Right.
Yeah.
Right. So basically, we're excluding 0. So we do this fanciness with interval notation.
And if you put a bracket around the 0, that's telling anybody who looks at your paper that you're including 0.
But we just said we can't divide by 0.
Can't divide by 0.
So that's not the case.
No deal.
Also, I kind of screwed up on this parentheses here. Make sure you distinguish, like if you accidentally wrote a bracket, and then let's say you want to change it to a parentheses.
Okay.
Like, what is that? Is
Yeah,
that
I
a
don't-
bracket? Is that a parentheses?
Sideways smiley face.
Yeah, so please erase. Here, let me be an example. Please erase when you mess up. Just get rid of it and then start again. Here, I'll make this. I noticed that issue on the last test.
Yeah, because is it or isn't it? I don't know.
And it's very important. Like, it's not the same thing. All right, let's move on.
Range then, the range on this graph is all the y values, and as you're noticing with this particular graph, hey, all the y values are positive.
Right, because if I take any number and I square it, that makes it positive.
Yeah, it doesn't matter what number you pick.
So what's going to happen is we're going to end up with, can we have 0?
Again, I don't think you can include 0.
Right.
Because you're really close to, but not quite touching.
Yep, you get closer and closer and closer. Now that means that we have, what, if it doesn't ever... Where do we want to go?
Well, let's go to continuous.
Okay,
then. I mean,
continuous.
we'll just keep the same order here.
Is it continuous?
It is not continuous. Why? We've got that domain issue at 0. And anytime you have a domain issue, continuity is not happening.
It's not possible. So we have a discontinuity, and let's say where it's at. It's at a certain x value.
I know.
What?
0 when x equals 0.
Right. There is a discontinuity at x equals 0. So that's an appropriate way of writing that it is discontinuous, but specifically where it's discontinuous at.
Okay. It's at 0. Yes.
All right. So next, asymptotes.
Asymptotes. There are a couple.
A couple.
There are a couple.
Okay. So vertically.
Vertically, x equals 0. That's where our domain issue is.
Okay. And then how about horizontal asymptote?
Horizontal asymptote will also, in this case, be 0.
Right, because it can't ever get below that.
Can't ever get below that.
0.
And again, your range helps you determine that one.
Right, because that's what stopped our range.
That's what stopped it.
How about extrema?
There is actually no extrema, although if you look at this guy, you may be tempted to say on the little curvy parts in there that there's an extrema, but
there's not. You have to actually have.
You gotta have the bump
or a valley.
Yeah, gotta have the whole bump.
You can't go halvesies.
Can't be some kind of cool curve.
No.
It's got to be top or bottom.
Increasing, decreasing, or constant.
It is. You know what? It's increasing.
For a little bit.
Yes. Specifically from negative infinity to 0, but not including 0.
Right, because nothing happens at 0 on this graph.
There's
so
nothing
we would
at
never
0.
want to put a bracket around 0. So increasing from negative infinity to 0.
That's okay. And then it decreases from 0 to infinity.
Right, the other half of I don't know why I wrote decreasing. Okay. I mean, D stands for decreasing.
D stands for decreasing,
But we
Same
need
reasons.
to distinguish from domain. So decreasing 0
And
to
all of
infinity.
these, when you're talking about increasing and decreasing behavior, you're talking about what your y values are doing.
Right.
And
you
then
list your x values.
You list the x
from
values.
From the x to the x, but you're talking about your y values
What the y
going
values,
up,
yes.
or your y values going
You got it. You got it.
Okay.
Are we bounded?
I think we are bounded below.
I agree 100% with you. There is a floor that our graph simply doesn't go through.
Right.
Bounded floor or bounded
below.
below. So here's a chance to model some quick
erasing
action.
Bounded below. What did I just?
I picked there you go. Bounded below.
Okay. Symmetry.
We have symmetry with the y-axis.
That's y-axis symmetry, because you could fold it on the y-axis and it'd be the same on each side.
You know, like folding wax and smashing down or whatever. Did you ever do that with wax paper? Just me?
I'm trying to spell.
Sorry.
It's okay.
Y-axis symmetry. And then lastly, but not leastly, in behavior.
Right.
Very important that we understand how this works and what the limit rules mean.
Right. So in behavior, as x
approaches infinity.
Yes, the limit.
The limit.
That's what LIM stands for, by the way, is limit.
In other words, the limit is that whole game you played with your siblings in the car on long car trips, you know? How close can you get to them without touching them, but still make them go crazy?
Like the whole, I'm not touching you,
Yes,
I'm not
that
touching
one.
you, I'm not touching you.
Yeah,
Okay.
that one.
Yeah.
And when your parents are like, stop touching each other. And you're like,
I'm not
touching them.
Yeah.
That's the limit.
So as we go to negative infinity on our function, we're getting closer and closer to a y value of 0.
0.
It doesn't matter that we'll never get there. We're saying as we go towards negative infinity, what are we going to get closer to?
Right.
So that's the limit part of that. All right, how about x approaching positive infinity?
Same thing, as it
thing.
turns out. And you can look at your graph and tell what does it look like the graph is going to touch, and it looks like it's going to touch 0.
It does. It looks like it's going to touch it. It never does, but it
never
looks
does.
like it.
Yeah.
Okay.